Hello, everyone. Today we're very happy to have Monica Kang from Texas A&M, who will be telling us about index from a point.
Thank you very much for inviting me. Today I'll talk about mainly this first paper that we put it out. And this is the output that my collaborator has fed into Notebook LM, I think, it's an AI. And this is how it visualizes to be like that. I thought it was very fitting as like that's from a point. So I put it as that. And this paper, we will highlight it by the end of it, which is going to come out today.
So that's the index, and then it's index from a point.
Yeah, I guess it's what's visualizing it.
Okay.
Don't ask me. I am not the AI. Amazing. This is also by the same AI that put out this, I think, is very well fitting. So,
islands are these days not that exciting.
We're not going to do islands, don't worry about it. We're not going to actually talk about Lagrangian descriptions. The highlight of this is that for the last, now about already 3 decades, since the Argyres-Douglas points at 95, what we learned is that one of the key points from quantum field theory is that conventional Lagrangian and path-integral formalism that has been really helpful in understanding various different mechanisms, but it does not actually capture the full landscape of consistent quantum field theories. And instead, we have like a wide variety of inherently strongly coupled theories, and so-called those are usually described as non-Lagrangian quantum field theories. Meaning you have a vast majority of consistent quantum field theories that does not necessarily have Lagrangian descriptions. And I guess it's described as these. And a lot of those are that we're going to discuss today are the Argyres-Douglas theories, and I guess the AI really made a pin mark of that as well. So also important thing is that we know that standard conformal data, like scaling dimensions, operator product expansion coefficients, are actually very highly redundant, which also poses a very difficult challenges for us. So then a natural question that I'm going to assess today is that, is there a more general formulation that we can have for quantum field theories that can encompass both these conventional Lagrangian theories and these new non-Lagrangian difficult theories in somewhat equal footing, and we can access them in more universal ways to understand their behaviors. So attempts to conform field theories from this type of ideas are using imposing constraints. As constraints, then we can have explicit understanding to how to bound them, and that will be a way to describe what can be possible. And in quantum field theory, we often use symmetry conditions or consistency conditions like unitarity and many others. And through this way, we can hopefully try to yield a universal constraints on the spectrum of the theory or the correlation functions of the theory. So these are all part of the conformal data if you deal with conformal field theory, or a generic quantum field theory that you can have imposed with a symmetry property. And by this way of doing so, we will impose very powerful model-independent type of bounds that apply to universally to any theory we can deal with, that explicitly shares that type of symmetry. Now, a big caveat coming from that is, while this is very powerful and universal, universal comes with its unfortunate the other face, that it does not going to work for any sharp bounds for a specific conformal field theory or specific quantum field theory. So if I want to understand a specific theory, that this is what we need to actually develop and analyze, this is going to fail drastically because universal is good and bad at the same time. So then the question is, how are we going to do something like this? If I want to really put in the equal footing, the best part of Lagrangian is that utilizing Lagrangian path integrals and variational methods and many others are specifically for that given theories, and that's the power of it. This is not identical at all. So today, what I'm going to really focus on is I'm going to utilize as much geometric point as possible, as index from a point should apply, to make these to work towards individual specific conformal field theories. So as we're thinking of conformal data and constraints, something like this program has been vastly used in the last 2 decades coming from conformal bootstrap, more coming from the universal methods. And this has even longer history. Like in the 80s, we had the VPZ middle models in 2D that worked specifically in that type of arena. And from the bootstrap, 3D critical Ising model or ON models were very powerful for that because the bootstrap precisely determined their spectrum and correlators. And this is the one that I did for the critical Ising model from these physicists. And this blue is the allowed regions of the conformal data. And through this method, the Ising model that sits in that corner with box. These are the scaling dimensions of these type of operators, and that's the scaling dimension of these type of operators. It's Ising model, it's very specific, so it's a much more less data, and that's why something like that could have been still possible despite difficulty. And this is utilizing high numerical powers to make these work. So what does this really tell you? Well, they have even more graphs than this. So the boundary of these type of shaded blue and allowed regions in the conformal bootstrap. These physicists have been able to then reconstruct of the spectrums of the theory via the extremality of the functional methods. As extremality is then the methods that you can actually pinpoint for a specific field theory that you're actually utilizing, whereas before extremality is done, it's a full moduli of anything that it would not be able to tell you for that specific point. So think of it like field theory standing at a specific point that satisfies the physical extremality condition is a way to think about it. So what is a common feature that we can utilize? Because if you want to really deal with more generic non-Lagrangian theories, especially including Argyres Douglas, it's a lot more complex. So maybe we need to cap out some of the S's that we can think about in general. So what I would like to really think about here is that there's an emergence of decoupling or vanishings in the space of the conformal field theory data, so that it severely constrains the spectral properties and dynamics. And if that is done really well, is how we can really say to specify the conformal field theory of our nature. So it's about how well we're going to deal with extremality and how we finally propose the decoupling that one can do. So what is the OP of local operator that we usually think about? So let's say we consider maybe that's not it. This is consider the OP of operators, then you should be able to get these with all possible generically available prime that's compatible with all symmetries that are imposed in this type of theory. But what this decoupling really means is that sometimes we discover that the expected double prime that's supposed to be always inherently there is absent. And this is what I meant by decoupling or vanishing. What that means is that either the operator is absolutely not there and non-present, or the coefficient is explicit vanishing. It's a very powerful and unexpected thing that can pinpoint how special this theory is. And this is the way to actually define theory defined as the sitting in this extremal function. And this is a type of logic we're going to try to utilize in the scope of non-Lagrangian theories today. So if you recall that from the last slide, that you have the bootstrap, so have the boundary of allowed regions in the conformal bootstrap, to then reconstruct the spectrum using the extremal functional methods. So what we need to impose on top there is that you can observe coming from there that at the boundary of the allowed region, like at that blue shaded region, there's usually a OPE decoupling that happens. So what is really needing as in between of a step that we need to think about is that there's explicit OPE decoupling that is shared in between that can go as an explicit step. And this is how we can maybe try to utilize more generally to oppose in from the overall type of phenomenon to the explicit reconstruction of the spectrum and pinpointing the field theory data.
The boundary is the exclusion.
Yeah, the full excluded, the conformal data realm that it
The
exists.
exclusion is it's
Yeah, think of it like it's like a modular that's sitting like this, and then you're pinpointing from this decoupling and where it sits.
but the region that you're excluding in the bootstrap is not you can improve it, right? It's not a shot, it's not a what so
we're learning this feature And you're going to do a lot more than that to apply to, of course, 4D theories. You're not going to exactly follow
But the
this.
boundary can be improved, right?
Yes, it will be improved.
If
You're
you
going
are,
to-
if like you make smarter choice, maybe right? It's not a physical constraint.
It is usually they're given as like a consistency condition that is not physically imposed, and that makes sense with the physical condition in the end that we learn about, but it's not usually deduced from that. Right, but this is the type of logic that we're kind of deducing out. We're going to use this logic to try to now build something like that in the context of actually more generic 4D.
So
Yes.
you mean you already made the smarter choices, but what was your answer to the question?
Smarter choices.
But there is no implementing.
You'll actually see how we're gonna do. We're actually not gonna make these choices, but instead you're going to try to use something of the that's going straight to more decoupling data. Because in reality, I'm not gonna do analytic things and go straight to algebraic data with operators. So I'll be able to actually bypass that.
But the decoupling is not, it's not a bound. You know, it's going to be a sharp statement that it's absent.
The
or is it a bound?
OP decoupling is also coming from the bound, or it can give the bound in terms of spectrum. Because these are, think of it like this, like a null state or null relations of the control field theory. So then it can give the bound of where it can live, or the bound can sometimes give you this. It's not necessarily always if and only if, but it does necessarily give some version of a bound.
But is it a bound on lambda? Or or are we going to tell us that
It's definitely going to give bound on lambda for
Okay.
sure. That's the null state.
it's a bound on lambda?
Yes.
Okay.
So that's the null relation in null states. Or the operator is vanishing, which is. Then the question that we should ask here is that and how much of the information of a theory can be then possibly recovered from the OP decoupling? So from this type of logic, I'm going to really focus straight to the OP decoupling. There's a reason I colored in red. I'm going to try to bypass everything to go to this data directly. And from there to be able to pinpoint down the CFT so that we're really doing like a bootstrap of OP decoupling from geometry is how we should really think about throughout the remaining of the talk. So what I'm actually trying to do is then we're going to explore whether the decoupling itself that we just talked about can be elevated to a defining characteristic of a specific superconformal field theory. Meaning decoupling is really sitting at the extremality point, and oftentimes might have a little wiggle problem, but almost. And maybe that's enough that there's only uniquely SCFTs or not as many SCFTs that can sit there, so that in turn, unlike the universal bootstrap like that you can do, it'll actually tell you what that is. So this is a pure bottom-up approach. I don't use any string theory throughout the talk today. It's going to be only field theory and utilizing geometry to define like this, because can't think of any other way at the moment that's more clever to put Lagrangian and non-Lagrangian in the same footing.
Externality of what?
Extremality condition as the decoupling.
But what externality of what?
Full moduli is the extremality, right? Like the extremal condition is then identical to somewhat of the null relations or these OP decoupling conditions. Sometimes it's not enough that you need more than that, but it might be much better to describe a specific SCFTs.
But what gets externalized? The index, so.
No, extremization is coming from good way to think about it is that it's the one that actually pinpointing what type of a condition that it has to satisfy, and that is identical to null relation. Because you can vary that. So that extremality is like where it sits to satisfy a very string.
So whatever is giving lambda equals 0 is the extremality condition.
Right. Or near that. So similar phenomena can happen in 4D n equals 2 theories. In fact, for certain 4D n equals 2 SCFTs, it has been observed in these two papers to see something similar to that of some sort. So today we're going to consider 4D n equals 2 superconformal field theories because it's not simple like n equals 4, but it's still manageable unlike n equals 1 because it's still algebraic. Because I cannot deal with it more generally as n equals 1 because the OP data itself is much more harder to grasp. The main conjecture that I'm going to present throughout the talk is that for then 4D n equals 2 superconformal field theories, the particular limits of the superpartition functions can be entirely constructed by either considering the decoupling or identically a vanishing condition in the very spectrum. And people who are familiar with it, particular limits of supersymmetric partition functions, I mean Schur indices and Macdonald indices. So the proposal is that we're going to translate this decoupling and vanishing condition as specifically the nilpotency relation. So for example, we can have x to the n to 0. Now x to the n to 0 is simple, right? It's naively describing the point at x equals 0. But you should really view it in the context of the full polynomial rings. So then you can have a richer structure imposed by this explicitly as a nilpotent relation. And this is how I'm going to be able to grab the spectrum and have to pinpoint this field theory. So then this is why it's indexed from the point as the title. So this is a spoiler. This is the main thing that I'm going to get to. It's a proposal that I wrote with my collaborators brilliantly, Craig, Lawrie, and Jaewon. So for here, we have a very precise proposal that for these 4D n equals 2 theories, where there exists a bifiltered ring such that the Macdonald index is given as a Hilbert series of the graded associated of the jet scheme or the arc space of the quotient ring. I will explain individual symbols. I'm not going to accept questions on what they are. I'm going to go through it very slowly, one by one, defining what that means. And the Higgs branch of that is given as the reduced scheme of this ring, so that it'll go back to the variety, which is very reasonable from what we want. So the goal of the talk throughout is explain what the hell this actually means, to break it down to you where that comes from and what that means, and give evidence that they hold in really a variety of classes of Argyres Douglas theories. And then there will be a little bit more after.
Do you understand? So QQ could have been PQ. What I get on the left-hand side?
It's not, well, we'll get there. I'll accept that question and the around there, because if I describe now, I'll have to describe all the rest.
And then just to make sure that the claim is clear, given evidence that they hold for many Argyres Douglas SCFTs. So what's the many?
So this is what I explicitly computed as Argyres Douglas theory. Our proposal is more boldly bishop-bold colors.
I see. So it's just check
So
the
I only
classes. There's no counterexample, but also maybe no general.
Right.
Oh.
This is a proposal, not a theorem. We couldn't prove that at the moment. It's a very bold proposal. I understand that proof is going to be very difficult. Any more questions?
Is there going to be a physical interpretation of the ring R?
Yes and no. You should ask that question once again when I talk about it, which will be the first next week.
Is there any construction of the ring R?
I will actually explain it to you, yes. And I'm gonna actually give like some highlight of a few very representative examples. I'm gonna construct it very specific. Yeah, I don't believe in good any theorems or conjectures without examples. Physicists, that's what. Lovely. So spec R is an affine bifilter scheme, which reduces the Higgs branch, is really the point I should remember throughout the talk. Higgs branch is much easier to be done, and this is always necessitated to hold when this holds. So really the important part is producing this, which is what I'm going to do next.
So you assign VOA to the Higgs branch? No, I'm sorry.
You could, and a lot of people do, but using in this particular way, you don't actually need to, but I'm going to compare with the results that actually use the VOAs, or sometimes you use that results to make computation more easy. In fact, there's a bifilteredness is not guaranteed by the VOA. It's going to explicitly show that they're not going to match for those. But the ring, of course, needs to match. All right. So what is this ring? Is a bifiltered ring? So I'm highlighting here. I'm going to track it individually to know which one you're actually talking about. So a bifiltered ring is equipped with a sequence of subgroups, and I'm going to write like this, such that it satisfies these conditions. It's basically so that things are under the inclusion and you can actually define to the next orders. So as long as these are then well described, the sequence is completely well described to be given, and this will be giving a two different filtration as P and Q. And then I'm going to give you a simplest example you can think of in mind. So you have two coordinates. So then you can write explicit of the subgroups on the ring, and that will be given as all the polynomials of the now degree that carries two different degrees that is going up to P and Q. Is everyone good? Subgroups are being all in the end together is not, but subgroups are. Now, I always believe that if someone is defining something, something has to work well. So I'm going to now give you an explicit, a simple construction to make it work. So a simple way to construct a very explicit bifiltered ring is dealing with the first this S. So it has n different coordinates, and I'm going to call that one to be having the bi-graded ring, and then give you the bi degree as A and B, and individualize. So then, since it's bi-graded, it necessarily decomposes to give you subrings, and I can write that very precisely with the bi-gradings. Now then, I'm gonna let the ideal to be not necessarily bi-homogeneous for these, so that you can write the then explicit quotient ring, and then because it's not homogeneous, meaning then it's gonna have this inhomogeneous, so that it'll mix degrees. So then this is not necessarily going to be bi-graded. It's gonna kill that type of structure. So here's an example. So from the CXY, I'm gonna now give you x squared plus y cubed, and it's gonna have a degree x on the x 3, 2, and y 3, 2, 1. So it's bi-graded, right? So then x squared will have a now by degree 6, 4, and y cubed will be 6, 3. And you can see one direction is homogeneous, the other direction is inhomogeneous. So generally that's not bi-homogeneous. In fact, throughout the talk, most of the things that we were going to explicitly give you is that one direction is homogeneous and the other one is not. So this explicitly destroys the bi-grade. Then now you can define a bifiltration structure on this quotient ring to be explicitly given as the image of the one that we already have. And that will be explicitly in R. Are we good? Excellent. So we're going to use this construction ubiquitously throughout the talk. Now, you probably may have noticed that this is somewhat problematic. This is a bifiltration. But Hilbert's series is defined for graded rings, not filtered rings, and we explicitly destroy the gradings. So then, if you're dealing with them, you will need to do something to recover the gradings to do any Hilbert series on top. So what does really Hilbert series do of a polynomial ring? What it does, it really counts explicitly monomials of particular degrees. And what that really means is that you have the existence of gradings that explicitly tells us what that degree should be. So in a filtered ring, of course, we explicitly lack that concept. So we need to deal with that by finding a way to recover some version of the grading explicit to work in that aspect. So how do we actually make this work? So that is where this GR is for, to give this associated gradings. So this is called associated graded ring. So what is that? A graded ring has an explicit decomposition that we can write like this. And we have a bifiltered ring, not a bi-graded ring. We don't have the grading at the moment. But we can construct explicitly a possible associated bi-graded ring, and we're going to have GR of R. And how we do that is we can write that as the substructures with that explicitly defined like this. So what it really intuitively does is that we're reconstructing the order PQ from the ones before. And there's the most natural way to do that, and that's associative. So then now we recovered a bigrading that is may actually not be the same as what you really originally started, but this is the bigrading you will explicitly get from by having Gur of R. Again, I'm going to give you an example because it's a lot of abstraction. I'm going to recover this that we started with, the CXY. It's not very illuminating, but the simplest example that CXY kind of has a natural grading, and you can see how it recovers that. So this was the explicit thing that we started with. Then you can write the Gur of this. So what it does is that before here we have up till PQ, and by taking Gur, it recovers explicit of the PQ, as I was saying earlier. So it's really explicitly recovering the most natural bigrading that we did not have before. Is everyone good? So from here, then can write the Gur R with a degree and recover the natural degree that we would expect of x and y to be 1, 0 and 0, 1. And you might say, that was very stupid. That's because it's the simplest example. Can you imagine, start with a much more complicated one, so it'll be much more complex. So now we established bigrades. So then you should probably ask, why are we doing this? Does that actually have a physical meaning than just this mathematical structure, which goes back to, I guess, your question on what does this ring really do? So this bigradings then come with the two. The first one is kind of like a conformal dimensions or scaling dimensions. And the other grading is right as a stress tensor. It's the Macdonald grading. It's a stress tensor, like T filtration type of grading. So you can imagine these two are the really important thing you need to have in the context of conformal field theory to be able to specialize to that theory point. But if you notice, we have 3 instead of 2. You have 3 gases. We've only given bigrading. So where's the third one coming from? And why do we need that? That is coming from the other symbol that I haven't explained to you. This is called the jet scheme. So we're going to start by considering a polynomial ring. So we have the coordinates and the generator of the ideals. Once again, we're not assuming any filtration to have or grading or whatsoever. So it's a generic thing. Of course, you can have filtration and stuff, but you're not going to need any of that. And these are arbitrary functions once again. So these are the generators, and I do not need to impose homogeneity. So it can be homogeneous or inhomogeneous. So now I can write a power series of that. So these are the ones that we're a power series in the coordinates. And these are the ones that are power seriesing up to the order of that. And in respect to that degree from the generators of the ideals. And you can do explicitly of the both. Now, then we can define a new ring. So that this is up to the nth order. Notice that there's n. Then you can write the this particular ring now that has up till nth order of all of those, and the ones that are up to that order power series that are up for the ideals, the generators of the ideals as well. So let's say if your x is a spec r, then the this Jn of r is the coordinate ring of the nth jet scheme Jn x of x. So it's quite a mouthful to call coordinate ring of the nth jet scheme. So I'm going to call it the jet ring and abuse the notation. Are you okay with that? Good.
How should I think of these more geometrically? Is there a picture, like a formula?
Think of it like it's called jet because there's a singularity. So what you're really doing is that nth degree is taking the deformation and variation away and away and away. Like the first jet scheme should be then think of it as the total space of the bundle, the space, so that it's kind of increasing and increasing and increasing. So from a point, it's shooting out a jet from the singular point, and it's giving rise as like a fat point, with a more hazy point.
So deformation theory would be going from one jet scheme to the next.
Right, so it's gonna go to all the way to infinite. Okay. That's correct. It's a total space from the template bundle. Yes. Yeah. Yeah, it's like I don't know. I personally view it as it's like a shooting the jet effect. I don't know. I think the name is kind of good for that. So we just now have done this. I want to say n is strictly a positive integer, and phosphorite does not push to infinity. So this is then naturally a graded ring with a jet grading alpha. This alpha is naturally given by having this explicitly pushed out. And this is the degree of the jet. That's coming from how much it goes through as this n into the alpha. So then what is this jet grading really does in this aspect is that because it's pushing literally outwards on how its derivative goes, think of it like it's the derivative. So it's coming from your CFT operators. These are the descendants. So you can think of it kind of like how this is imposing further out than out, which is what we expect from the CFT from primary to the higher descendants. So note, if this R is bifiltered, which is what we have, then Jn of R, this jet scheme, inherits the bifiltration. So then we have the inherited bifiltration, and additionally we applied another grading. So we have jet grading. So you're actually having a trifiltration, which is not a generic trifiltration, it's a specific type of trifiltration on this jet grading. And to push it to infinity, what we really take, so you're take this specific thing as a coordinate ring of the arc space when that is pushed to the limit like this. So you're taking the inverse limit of the Jn of the x, and then as the direction changes, it goes to this direction. Yes.
Does this usually stabilize for infinity? Because I would imagine that if you're comparing this with descendants, then it's at some point you're going to get some worse.
So physically, you're probably commenting on the fact that sometimes you're hoping that it's already unique enough to go to the but that's a different question from is it stable at the infinity, right? That means you can infer that it's stable at infinity, but that does not mean it does not exist. So the higher descendant has to be encapsulated to go to infinity. Yeah, of course, physically to actually compute these, both for physics or math, we can do infinite n. There are different techniques that recently mathematicians have been developing. I think there was a paper last year and 2 years ago that used for specifically A2 theory that used without the Bruckner basis or anything and analytically actually computed J infinity, but A2. So it's very preliminary, but there is such math. It's work in progress by a lot.
So the limit exists for any bond.
Correct. So once again, these are great. I believe in examples so I have to see how it works. Let's consider that. And this is the same example that I started with. That's very simple and illuminating. So you have 2 degrees, 2 pi degrees of the coordinates. So then from here, you can explicitly find the coordinate ring of the nth jet scheme, or in short, jet ring. And this is the first jet scheme. As you can see, that's the t to the 0 and linear in t. Second jet scheme, you have now 3 relations because we need the t to the second, and you can see it will go grotesque very quickly. You can compute it continually, and you can get for a generic sum n, not infinity, so it's finite n. Can explicitly write that if there's an ideal that's generated by this relation with the coordinates x's and y's. And you can compute it accordingly, and as you can see, computation will not be easy as n goes higher. But it's a very explicit and concrete object that one should be able to compute explicitly when you're given with it. Remember, when you're taking commutative algebra, I didn't really need more to go beyond to compute this object now that we've established. And this is the one that then completes before taking Hilbert series on what the geometric object is. Note, it's really geometric object. It's an arc space as it goes to infinity. So all we've done thus far is having this object that we concretely described. This was bifiltered. And this is trifiltered. But here we don't have any gradings, right? We discovered that while we have an explicit filtration to the geometric structure, it doesn't necessitate the gradings. And this Schur is the one that's giving you associated graded ring for it. So now it's tri-graded. And this, among the tri-grading, the other two were coming from the two gradings. As I said, physics-wise, you think of it more like a normal dimensions or scaling dimensions. And the other Macdonald gradings or stress tensor gradings. I wrote as T for a reason. And this Q was the one given by this Schur that's coming from the jet grading. Now, the proposal then explicitly is that this is the one that's coming from geometry. And this index from a point that it gives rise to is explicitly the Macdonald index for individual for the n equals 2 superconformal field theory. So that necessarily we need a bifiltered ring, meaning you have a quotient ring and the bifiltration together to give rise to this as a geometric origin, distinguishing individual theories. And that's how we're going to be able to analyze as an individual data of how to distinguish them apart, like what we can do for any then CFT of this type of fashion. And now we're going to answer Max's question. Can this be any P? Mathematically, you can do something like any P, but it would be not as illuminating to be identical to Macdonald index. And this is where the equality comes from, because you want to take the descendants to be the given by these as differentials. And if this is graded independently, that's going to skip as a different mismatch of the descendants. But to match the identical descendants to give rise to it, you're going to put that identical to the first scaling dimension grade.
The PQ is just physics.
That's right. And you can do that, but it would be not so illuminating. At the moment, I guess you don't know how to compare yet, because for that, you don't know how to completely bifiltered ring. You will actually discover how you should have done that for even very difficult Argyres Douglas theories. We are only half mark. There's a reason for that. So bear with me. The first thing you should probably looking at this is like, oh, that's quite amazing of a proposal, but it looks also very difficult. So there is both technical and conceptual challenges. So technical challenges that there's J infinity. Arc space, the infinity is always difficult, as we know, in any context, math or physics. So it has infinitely many generators and relations. That's very difficult. And also it has non-trivial syzygies. So meaning we have to always compute in the Grosvenor bases, and for that, as infinity is not possible. And conceptually, how do we determine this R for a given quantum field theory, which is connected to what Inan was asking as well. So for the remaining of the part, we're going to go over how do we massage this or to work with a given different type of examples and such, and how we can think about it to generalize it accordingly. So first, dealing with infinity, since I always find technical challenges a bit easier than conceptual challenges. Once again, J infinity has infinitely many generators and relations. So is there a way to just compute to finite and be done with it and not worry about it? So suppose now we have a ring with n different coordinates, and we need by degree, so we're going to have this degree. And then we're going to have a quotient ring with this ideals. And that will be the generators of the ideals will also be then by derivative, because we have bifiltration. Now, what will be then order by order contribution? Because that's the one that we'll need to analyze. We want to truncate into some finite things to understand up to that level. So this is the jet grading, remember, of the alpha. This is the degree of the jet that we need to impose, and that's the one that's going to tell you how much we'll actually need. Now, it's graded with respect to this first, that's coming from the first of the by degree that we started with, and this jet grading together. And on top of that, we need the one coming from the second grading and the stress tensor that we start with. is the lowest order contribution that we get. And you can do something analogously coming from the ideals. So for here, we're gonna have now coming from C, and then the same degree, and then the stress centers come from the second degree. What I mean by that is, if you now look, they started in here. So if you're coming with earlier like x squared plus y cubed and these, then you could have 6 coming from here and then 5 coming from there. So you would need an 11. So you have to consider at least 11, something like that. So then you'll need to consider this getting rise to the order of that, specifically like usually L. Then what is L really going to be determined by? Is that coming from considering L minus D number of orders of the jet. And D is given as the xj with the smallest first degree in the ring. So then you can truncate it to here if you want to only look at up till that order, which is presumably good enough. You don't expect anything weird to happen after.
But this is, you need to explain that it does stay there.
Right. Yeah. Like for example, like earlier 6, I will do an example. So
In fact, we're just saying that without you only need to compute it. In fact, like order by order. So just on paper, the final order.
Sorry, the thing is then that for the leading terms, I'm interested, this is the sufficient approximation.
we'll do an explicit example of that. So let's go to that discussion after. So here, what we are really imposing is that we can compute to arbitrarily large order over then finitely generated rings.
Mhm.
So how do we find these bifiltered rings in the first place? So before anything, we need to have those rings to be explicitly computed. So recall that what we are proposing is that we are having decoupling in the space of CFT data to rise to a source of a deep information of a CFT. So for our interest of 4D n equals 2 SCFTs, where we have explicit short multiplets that will generically appear in the OPEs of the operators are in fact absent, is what it really means as a decoupling or vanishing. This is an explicit example. So OP of the stress tensor that's from the C hat 0, 0, 0 is a Dolan-Osborn notation. If you're unfamiliar with it, it's a specific type of a multiplet. And for these, we normally contain this to always happen. But this multiplet is shown to be absent for this type of Argyres Douglas theories. So these are the type of things that I'm really referring to as decouplings that looks very unique, that might be helpful to pinpoint down these type of Argyres Douglas theories.
How do they know?
These are explicitly done by these 2 different groups. Very explicitly done. And it's being rechecked by many other people later. This is considered like a fact at this point. Now, this can be translated into algebraic condition of actually n plus 1 is equal to 0. So this is how it can then go on to trying to then build these type of bifiltered rings from these type of now translating into algebraic conditions. So here I'm going to borrow to consider explicit now examples for these type of theories. Something called SCFT VOA correspondence by these physicists and many follow-up papers after. So what that conjecture says is that the decoupling in OPEs in the 4D Schur operators, or Schur centers, that can be found by studying the null relations, something like that arises like earlier, in the VOA under these correspondence. The reason is because VOA captures all the chiral operator that goes under the Schur sectors, and that should be the one that's capturing all these explicit information is the reason. We're then actually consider the example of this explicit A1, A2, A2n Argyres Douglas theories, because these are exactly these type of theories that I just highlighted. So associated VOA here is known. It's n2, 2n plus 3. For physicists, this should not be surprising. This is a Biot minimal model. So this contains a null state at level 2n plus 2 in the schematic form of this. So this is a strong generator of the n plus 1, and this is the only strong generator that goes up onto the vacuum state. And in fact, this is exactly the stress tensor. So that in turn, this is explaining where the algebraic relation of x to the n plus 1 equal to 0 comes from. So what it really means from here is that we can study null relations in the VOA. And that in turn will give us the polynomial relations in the strong generators format. And from there, we can write as an algebraic relation to give rise to a candidate ring, R structure. So that from here, we can actually generate the bifiltered ring coming from that aspect. So that's a lot of abstraction. Let's actually go to doing explicit examples. Let's start with the easiest one. We're going to consider Argyres-Douglas examples because once again, we'll not focus on non-Lagrangian theories. That's really difficult. And we'll first consider where Higgs branches a point. That's the simplest possible decimal point. So this is a slightly more difficult example than what we just did. This is A2, A3 theory. And the VOA associated in general to AK, AN, as satisfied by the GCD condition, is a W algebra minimal model. And these are studied by these two papers first, and then the others after. And considering these explicit theories, we're interested in A2. So this is going to be giving the W3 algebra. Now, generating null relations are generally extremely difficult. But physicists are really good at the brute forcing and computing. So this has nicely been done. This is in the appendix of our song that gives rise to null state. It's a very long and gruesome paper. And they write explicit null states and write the relations. Pretty miraculous that one could have done that. And you can notice that these are the strong generators. The rest are descendants, strictly, so we don't have to worry about it. And I'm going to give them as x and y accordingly. That's L minus 2 and W minus 3. Then we can let the ring to be two coordinates with the bi-gradings. X is 3, 2, and y to be 2, 1. If you noticed, there's a reason why I started always doing x squared and y cubed. It's exactly like this one. Are we good?
Can you explain the grading for the degree of the line? Why is it?
So 3 and 2 is probably obvious.
Yeah.
And 2 and 1, you should be questioning how I got that. It's much more harder. I'm actually guessing that coming from the additional information of the stress tensor grading. To make it, but it's unique. You cannot do any other things to make it.
It's fixed by forming that?
To make as a correct grading to give rise to the sensible bifiltration to bi-grading that matches with the any Macdonald type of grade as a stress tensor grading too.
Okay, so you do in that proposal, you do match the grading from both sides to the distance.
That's correct.
But it's a bit chicken because they don't do the procedure how to do that. You say there is a grading that is happening.
I agree with that. In fact, W3 algebra on its own to give 2 and 1 is extremely difficult. You can do it. It's extremely difficult. It takes really a lot of tiring effort. And I'm going to hide that in the talk because then I will never be able to finish within a day. Now, you're going to consider the ideal of this. And it's necessarily inhomogeneous, as you have been seeing. It's homogeneous in one first direction, but not second. But this is the one that we get for the ideals. So let's move it up here so we can analyze further. So the bifiltration that we want on this ring R is the one coming from the induced by the bi-grading on considering the CXY after quotienting the inhomogeneous ideal that we just considered here. Then we get the jet ring, so that I can get the anti-jet scheme as explicitly taking that quotient. And the ideal is generated like this before, like the one that we talked about earlier in more abstract form. Now, to determine the Hilbert series, now here, this is coming from the log 6, and then this is going to give you 5. So like 6 plus 5 is 11. So to consider their mixing relations, so that it's going to consider all the syzygies, like the relations of relations, and all the mixing to be all taken into account. And we're going to make it 13, which should be strictly bigger than 11 and one more. So bigger than 12, so I'm going to have it 13. So by that point, if that matches, there's no way it's going to be different afterwards. So then we study J11 of R because L minus D is 2 here. And it has then this particular one has 24 polynomials in I11. And we use help of the Macaulay 2. I have to say, I never knew Macaulay 2 would help my life when I was taking commutative algebra in undergrad, and here we are. So I used to say this I will never use again, and I was very wrong. So I'm going to never say that again. So from here, then we can find the Grosvenor basis and do these computations very nicely. And while someone has given me so much difficulty for not getting Blackboard talk, this is the reason why. There's no way I can write this on time correctly on the board. This is what we get. In fact, we can continue further on. It actually doesn't, while it looks very gruesomely tiring to do so, even in Macaulay 2, it actually takes less than 5 seconds to produce this. And you can go to quite high order pretty easily. And I'm going to cut it here. The Macdonald index is not known beyond. And this is really identical to the index known from the same paper. And this is really, really difficult to do as a Macdonald index. This takes hours and hours to do. And you can see how nice it is. And with a very simple origin of ring and bifiltration, that can just generate something like that. So it's very powerful to know the geometric origin to encapsulate this and not do it brute forcing by hand. So thankfully, while W3 is very still difficult, and generally this is not known for W algebras, for this particular case, that we need to consider then to go above A3. These higher level known relations are also known by the same people in the appendix. This appendix is, by the way, very young. So let's derive the rings coming from there. Because using these individual relations in computing is actually really, really, really tiresome. And it doesn't serve the purpose of finding geometric origin either. So from there, we can nicely write this. I'm omitting how to derive this because it requires a lot more math. But you can explicitly write like this uniquely. The coefficients are very important. If you change the coefficients, it's not going to give you the same result. Their ideals are different. And if it's birational equivalent, they will also work. It's only working up to birational equivalence. So these are the rings that we derived. And from there, we can compute these. Once again, I needed slides. And all of these, Macdonald index is not computed of that high level. For the ones up to a known level, they know they are matching for any possible known Macdonald indices for these theories. And also these took strictly less than 8 seconds for individual. It's quite powerful. Geometry is always amazing. It is. Now that's really amazing. We really want to emphasize that. But known relations are often not known. I gave you a specific example that probably answered both of you guys' questions on the how we compute the finite n and how to make sense of that. But what if we don't have any null relations known? And how do we do for such occasion to give some validity check and how to actually compute them? So for that, I'm going to consider generic AK minus 1 and AN minus 1 theories, minus 1, just so that I can make computation more easily. And first thing that we need to then consider is that, well, first of all, they have to equal prime for the KNN. We need to write down explicit rings, right? So all known bifiltered rings are Jacobian rings here. So I can write with the KNN minus 1 coordinates with the bi degree. And then you can write explicit quotient ring by rote differentials, basically differential geometry seminar technically. And these are the degree n plus k plus 1 polynomial in the first degree, and the xi. Now, the null relations in W algebra is absolutely not known anywhere in the literature. So from here, then we can utilize the known earlier first few iterated coefficients of Macdonald index. And then that is usually enough to actually suffice the data here. So then these are the polynomials. And it uniquely fixes the rings, actually, surprisingly. It kind of also invalidly checked the Macdonald index was not crazy, and that was enough sensibility of that powers. And no, a weird number that's coming from the birational equivalence. You can make it more than one coefficient and make it wrong. But coefficients are important. It's birationally unique. It will not work anywhere except this. So this will be the prediction coming from here as OPE decouplings. also known as null relations for these type of theories. And you can see it goes even all the way to A2, A10. You can actually do more than these, but these are the ones that's already out in my paper. That's already published. And yes, we have a lot more examples now. Now that's very illuminating, but I want to consider the Higgs branch from a point. Just really staying true to the fact of index and point. But that's not good enough. We want to consider a Higgs branch is non-trivial and it's not just a point. So let's consider those examples. So one of the most illuminating example of those kinds is the A, D type. So these are the A1, D3 geostatical series. These are well-known, notoriously difficult. And around the same time of our paper, it was also studied coming from the Jou's algebra, from number theory techniques to understand these type of theories, all around the same time, summer of last year. So it's very recent. So this is the ring that you can write. Note we have 4, so it has a quad grading that I'm putting explicitly. XYZ is the original gradings that we write as 1, 1. So that here, the bifiltration what we're getting is once again after quotienting from the inhomogeneous ideal, and that's the ideals that we're writing. And the new W is graded like this. Now the Higgs branch of this theory, you can easily tell from the Jou's scheme or just glancing at it, is C2 mod Z2, which means we have an additional SU2 isometry. And what that means is that the ideal is homogeneous under an additional grading, so you can get these according. From that, we can explicitly generate this. Pretty shocking. In fact, like looking into the 3 + 1 and all of these are coming from the flavors of this SU2. And these decompositions and everything, a flavor refined Macdonald index, all matches with the up to known orders of the Nilpotency, and it goes beyond. Quite amazing. I didn't do any additional input. It's just pure geometry of bifiltered ring. It works magically, even if the Higgs branch is not a point. Now, if you're familiar with our geostatics theories, there's a natural puzzle that comes right about. You have introduced a coordinate W that is not XYZ. Remember that actually in this paper as a Jou's algebra, they didn't do it this way. The reason is because it was SU2. The adjoint of SU2 will give you 3, and this will be XYZ. The coordinate range should be able to be generated from the XYZ. So then how do we make sense of this, and why is this reasonable as a ring? In fact, this W contributes as a stress tensor to the index. So why is that the case? In fact, if you do as this XYZ as the 3 strong generator, you can write explicitly as a ring like this. And in fact, this is isomorphic to the ring that I'm writing explicitly here, because our bifiltration here can be pushed to the isomorphism to the bifiltration of this R prime. So I can actually demonstrate and prove this isomorphism. That's the next. But this bifiltration is different from the one induced by the bigrading here. In fact, if you do this, the Macdonald index is not identical. Because the quotient ring itself is isomorphic, it does not mean bifiltration, which is additional structure on the quotient ring, does not need to be identical. In fact, different type of things that I take is different. So this one, just remember, this looks like something that's probably familiar to you. If you look at Macdonald index, for most of the things that Higgs branch is not a point. It has to be sourced from the stress tensor at the very minimum because it is a CFT. And because of supersymmetry or superconformal symmetry, you need to have the Sugawara condition satisfied. And what that means is that this needs to be put into geometric meanings. And here, W is playing that role very nicely. And also, this is the easiest way to write the scheme as well, the minimal way. And in fact, most common person looking at just purely algebraic relation will write like this. So introducing this W allows the bifiltration to be induced by the bigrading. It's a unique way of inducing. and the minimal way to do so. And this is how W plays a very important role, that this could not have sufficed to give rise to it. Now, as a ring, these two are identically to C2D. And this is known from both this paper and the paper before as a conjecture, which is actually demonstrated here. So what about the bifiltration structure from the DOA perspective? That is really a great question. I have no idea, because I know a certain limited number of filtration structures that it can give rise to. I didn't quite find the one that matches with this type of Macdonald filtration or T filtration that I call as. If you know anything like that, please let me know. I would love to know that. All right, let's move on. So we're going to now consider more complex Higgs branch. So up till here,
Think about dimension, real dimension.
we'll get there. Thank you. It's like almost as if I planned it. This is amazing. So I'm going to start with not inherently 4 coordinate examples before up to a third. So now go up in the dimensions. So this is the minimal one that's inherent 4. And you can go now higher up here, and that's going to go higher numbers. So this is the first one that I can write like that. So the degrees, as you can see, it's more complicated. And these are the structures we find. And you can see it's inherently 4, so you get 4 different type of gradings. Now, the reduced scheme here, easily it's x, y plus z squared. So the reduced scheme is exactly C2 mod Z3. And we know that this is known from the Higgs branch as well. So you can see this works very nicely. This Higgs branch is not a point. I want to point out that makes sense. Yeah. And you can compute explicitly coming from here, the full Hilbert space, the Hilbert series of that. And this is the one we find. And there's a reason why I chose this specific example to be portrayed. Because up to some minimal numbers, it has been computed brute forcefully in Bush condition and it matches up to that number and goes beyond. Also, this difficult looking example, they don't take more than a few seconds. It's really fascinating. You can go to like 40th order really easy. So you might ask them, why do you put the set? It's actually a half order, so it's really like 2. And plus, I don't think I could fit more in here. All right, so from here, then the question is, what was the bifiltered rings? And what did you find for all of these types of different theories? These are the all different classes of theories and different things, A, D as well. And there's more that we have done now, but all of these are explicitly computed by us. Once again, coefficients are the really important things. If you change that, that's not going to give you the right answer. Changing to 2, you're going to get the wrong answer. It's a unique number. That's very important. It's really specifying it from that. And Macdonald index for each of these theories seems to be recovered by the corresponding polynomial equations. For the ones that explicitly known has been all checked, it all matches. And the lists are now much more longer, of course. These are the only ones that portrayed in our already published paper, and work in progress and working on a variety of different type of classes and many others. So let me summarize. We propose the existence of schemification of the Higgs branch of each 4D equals 2 superconformal filters, which allows recovery of the full information of the theory, or at least the Schur sector and the Higgs branch, about the protected operators. The key object here was, this is the one thing if you want to remember, is a bifiltered affine scheme. That's really the key object that's sourcing everything here. It's coming from geometry. The Higgs branch is then giving us the reduced scheme, so it's going to go down to the variety. It's a more familiar story that you can easily understand. And here we propose that this bifiltered affine scheme is a really key object for a variety of Argyres established theories. I highlighted different type of examples and see how that can come about. But not limited to those, there's a lot more we have done that matches on all of them. And these are derived explicitly from the decoupling phenomena of the OPEs from the 4D superconformal field theories. And these are the one from the field theory to try to find the geometry origin. But this is very shocking and amazing. And when you're writing something like this, when I was having bold thoughts, you didn't actually know it would work this well, to be honest. I thought it would work well, but not of this degree. Which made me really think, then what is the really fundamental object of this geometry? And we're supposed to find the field of view, the reverse direction. So then we can first summarize and see how we understood from this way to try to find the reverse direction from geometry to pinpoints. And from the fanciness of this, you can probably guess this is generated by the AI. And I thought it was very well done. So I put it up in the top. So in the ring that we can explicitly define, that was a difficult part, right? We get the jet scheme and we get the arc space. But really what makes it so nicely geometrically well described to get the Macdonald index. And this is really highlighting what we did today.
Your jet scheme is Claudia. That's how usually AI thinks about the Claudia.
I know, that's unfortunate, but I thought it was still cute. So here comes the spoiler. This is supposed to be announced tonight. I literally submitted it yesterday. And what this is about, I mean, as the title suggests, algebro-geometric bootstrapping of OPE decoupling. What that means is that what you're doing here is actually much harder. What you're doing is geometry as a fundamental thing, and you're going to pinpoint the SCFT. So what we know are the schemes arising from these OPE decoupling possesses a moduli space of parameters like this. Also, it's fancy. That means I produced with AI. So what is the main concept that we needed to resolve? Is that generic points in this moduli space lead to the spectra that cannot be interpreted as n equals to SCFTs in 4D. So what's the requirement that we need to really think about? What we need is a physical consistency condition that is not coming from physics. It has to come from geometry. That has to come from purely geometric condition that has to make sense and truncate it to select the viable SCFTs from this larger space of geometric data. I think of it like a wiggling problem. So I'm going to wiggle around what is the correct answer. How do you tell that from geometry? So the solution is basically geometric extremization. So hypothesis that I have then here is that physical theories live at this extremal point. And extremality is an explicit given by geometry, the Betty numbers. So at these explicit unique points, the Betty numbers can be computed coming from the synergies, satisfy a specific and restrictive conditions that work for individually unique SCFTs. And that uniquely fits the moduli.
What is this moduli space? What is the moduli called?
The moduli space is the one that you can have as a full. Once you have a lot of these type of different things that you can have, you need to specify what type of rings that you're supposed to have and what type of question that you cannot go around around there, and that has to then satisfy different conditions because it's coming from geometry here, not reverse trying to put the geometry. So from here, we need to give the condition and that give ratios.
So is the moduli of the rings produced from what we define?
Correct. Right. And if you want to know explicit conditions, which actually write very precise geometry conditions, and this paper is, we tried really hard to make into PRL paper. It's 6 pages long with an appendix. Appendix is all the computations, so you don't have to see the condition. It will be explicitly written there, and it'll show up tonight. And given the lack of time that I already went over time, I'll end it here, and I'll be happy to answer any questions. Thanks for listening.
Thank you. Do we have more questions?
So first, come back to the VOA from
Notice I only gave a highlight of VOA using it first to the first example, and I didn't need any of those. So I started with the VOA when I was first dealing with creating this problem. So my historical way of thinking about it. So this is how I learned about the null relation to try to do it. But if you remember, once I have the bifiltered brain from different aspects, and I don't need it. In fact, the one with the Jou's algebra with the VOA is different from the one with the bifiltration and the Higgs branch is not a point. And in fact, that method doesn't give the Macdonald index, but my method does because it's lacking the stress tensor. So in a way, it already deviated from the known VOA methods. I do agree it should be eventually a VOA filtration, but I don't know the answer to that. That'll be an open question in math. And I don't know how to prove that at the moment because I don't actually know the filtration that fits. I probably need to talk to people who know like million different filtrations much better than me.
Suppose I filter R, filter ring.
But fixing the ring is very difficult. You see, the ring, so that filtered ring was already deviating from BOA.
What's that? Suppose I filter R, will filter polygon after.
So if I fix the ring particularly well, then you're going to get the right answer.
Brings it
Now,
up
the question is,
You can ask about the mapping, rings to SCFTs, is that mapping injective? Injective?
what I'm saying is that if the geometry of that's not out yet,
Mhm.
the condition is unique. It's actually necessary and sufficient, and for all the cases that we've done, it's actually for all the theories we've done, it's necessary and sufficient.
But it's a bijection.
Correct.
Right.
Now, I cannot claim that would be always holding for generic n equals to SCFTs. I neither prove that or could be that bold about it in my life.
In examples you showed them.
Yeah, there's a lot more examples, and it will be more highlighted probably in the paper that you'll see tonight. And there's explicit computation that's not contained in, but that's highlighted there. Everything that we've done works.
Probably a very fine, but you haven't asked for category. Like, is there some natural thing concept?
What is amazing with the question is that when I was explaining this to my own brother, that was his question. And my answer to that is, in private, I can be very boldly explaining my intuitions and be okay with being bold and being wrong, but not in the recorded setting. My official answer is like, I do not know. If you want to know, I can say after the recording. But yes, that's, I think, a question that my own brother asked, and also another person that I talked to is a professor at Texas A&M math program asked the same question as well. Thinking about it, I don't know yet. This was really hard. It took me a long time to even get there. Time will tell, is my guess. And if you have great thoughts, please tell me or talk to me. I'll be happy with any inputs. I mean, think about it as the following. The Betty numbers can be defined in two different aspects. And the really important is like those two combinatorial way and the topological way is matched by using causal complex. And then how you well implement that coming from the Hom system is very then the essence to make it different type of categorization. But yeah, all right, well, I'm gonna end there because it's being recorded.
So somehow, maybe there's some sort of practice.
I agree with that, because in reality, to do the Betty number accurately, you need to do the spectral sequence very accurately and to define what that means. So in the coming paper, we actually complete the Betty numbers and uniquely fixes them, but we don't address the categorization because I don't know it. That's really the reason for it.
All right, we have no more questions. That's like what I get.
Thank you.